Welcome to the speak. Contract first, session types later. My name is Marco Borst. I started programming before the internet. Actually educated as a electrical engineer. Nowadays Scala, but through Java.
So, and that's me, I'm Slava. That's pretty much everything about me. And I will just maybe stay here on the side and let Marco do the talk. Just introduce myself maybe a little bit more. Yep. So we started to work together with Marco on this plugin. So now you cannot hear me, right? Oh, now you can hear me. Good. So we started to work together with Marco on this Placewager plugin for Zalando. It's actually a great place to work. We've got many small teams, many microservices we implement, and actually we have this interesting API-first approach, which is a Placewager plugin as a code generation framework for. The API-first approach means we first have to specify our APIs, and first then we can implement them. Basically, we do this in Swagger. We take the Swagger specification, give it to developers, and developers then implement usually or often play code for the specification. But that's kind of stupid to do because, if you already have the specification, we can do better. So we can actually get this specification, all different parts of it, and we can generate a couple of artifacts. For example, play routes, tests, marshallers, controllers, validations, test data model, and like. So basically, what does it mean? We just take your specification, we generate fully functional, proper functional, RESTful shell, and then you as a developer just to have to take a Perl of your application, business logic, put it inside, and you have it working. Great stuff, right?
No, sorry, I don't think so. If we take a little bit of a look at what we are actually trying to achieve, we're getting from a RESTful specification treated as the single source of truth, and REST has this Richardson maturity model, a couple of levels. Most of the APIs that we actually know, they stop at level 2. They do not really contain hypermedia controls inside of the body, inside of the responses. And that is because all the specifications, they are more or less in a form static. If we wanted to go a little bit further, if we really wanted to generate directly from the specification, treat it as a single source of truth, we would like to generate it in a H2S, a hypertext as the engine of application state, a level 3 type of thing. Now, if you think about that a little bit further, you still would like to treat one of those specifications actually almost as source code. The rest should be generated from it. And then in such a specification, you have the definitions, the model definitions. You also have URLs, verbs, parameters. You would like to generate for that the server side, the hypermedia controls, and the MIME types directly from the model. The other way around, generate then from that the hypermedia controls and the MIME types towards the client. Client code can also be generated for a quite big part of it. The problem with it is that in specifications you need to add rules how to generate this hypermedia controls, how to generate these MIME types. And those rules are at this moment missing in almost all the specifications or the specification formats. There are a couple of different types of specification formats. Swagger is the most known. RAML, API, API, Blueprint also. They're all level 2 capable. So thinking about REST as, everybody thinks about REST as being stateless communication. But at the same time, we have all these problems with having stateful resources, stateful clients. The application state is maintained on the client side. We have stateful sessions. And of course, this was also what made the web such an incredibly cool thing. State is in H2S, the engine of application state. It moves forward in time. You can see it as a sort of interacting state machines. So, for example, we all know that an application we should enter actually only at an endpoint. So there's only one call directly towards the resource. The resource then sends a representation back, and in this representation you should have the hypermedia controls which advance the state of the application further. Client can select one of these hypermedia controls, sort of navigate it, and by selecting that, update the resource, bring it to another state, after which the resource can send another representation for this resource back at that moment. And only at that moment, the state of the application is advanced. So these arrows in between, they form the contract, a formal contract between the server and its clients. In HTTP, which is a uniform protocol, the client and the server, the resources, are actually completely decoupled. So there is no real contract at that moment. How do you enforce such form of a contract? How can you make sure that the state machines behave in a very well right way? How to ensure that right behavior? That's a problem which is already standing for a longer time. UBF, the universal binary format, which was invented by Joe Armstrong. Who knows Joe Armstrong here, by the way? Especially with akka and with the actor model, he came very much up. He, at some point, I think it was about 10 years ago, he made a paper getting Erlang to talk to the outside world. Joe Armstrong was the inventor of Erlang. And he didn't want to think anymore so much about programming languages. He wanted to treat processes as black boxes. At this moment, they're represented as white boxes with a B in it. And he was more thinking and more interested in how can you say something about the communication between those boxes. He invented there the contract checker. And if we map a contract checker on a RESTful way of communication, on a HTOS communication, you can think of the black lines as the moment that the request response. Communication is going forward and backward between the server. So the red arrow is the server time, the blue arrows is the client time, and a contract checker in between those communication would need to be able to validate that both work in the right way with what is actually going over the wire. For the client, that is pretty well easy to do. You can let such a client checker, you can see it, what set of hypermedia controls are being sent towards the client. And at the moment that the client actually checks it, you can check that this hypermedia controls was in the set. But for the server side, it's more difficult. There's resource state over there. So HTOS, in a RESTful web way, it only allows us to check the client behavior. For the server, we need additional information. Now, if you think of a resource and the state transitions that it goes through, it's actually very much close to what business rules define. So if we think, for example, of it as a parcel which is transferred to a couple of parties, you can think of this as a state machine of such a resource. And in such a specification, you can encode such a state machine. In this part, we extended the Swagger specification with a state machine specifically for the allowed transitions for a resource. States can be packaged, sending, moving, delivering, lost, and also the state transitions from one such a state to the other state. Visually, it looks like this. From this paper, UBF, the contract checker in between a client and a server is also stateful. It maintains a state machine of what is actually allowed in the ordering of messages going in between the client and a server. Joe Armstrong did this by adding a tuple towards the message which is going forward and backward. The message itself is just as we're used to, a request or a response. And the state is the state which advances the state machine of this communication. So in H2S, in a webful application, you can have state at different locations. And we all know that state is bad, but in a webful way, it's actually even worse. The state can be at the resource, it can be at the application, and also the web and the protocols, HTTP, it already gives us a possibility to transfer part of that state. So for example, if we're talking about state of the resource, the state can be explicitly in a part of the resource because it is contained within HTTP, but at other moments it's not there because we don't want it to be there, and then it should be implicitly inferred. On the other hand, the application state, which is maintained at the client, also there it can be explicitly in the HTTP protocol because it's encoded in the hyperlinks, or as especially 7-8 years ago was being done, a web session was maintained on the server side. So a contract checker to be really validating a contract between the client and a server, especially on the server part, needs to know this resource state and this resource advantage of state also. So contract checkers can be stateful, they need to be stateful, and they act at runtime at the moment that they are running. And yeah, that's pretty cool.
Yeah, that's not cool at all. That's not cool at all. After all, we're at Scala Conference. We don't want our RESTful API be stateful, certainly. They're supposed to be stateless. And we don't want anything to happen at runtime. What we would like to do, following. We would like to encode our state in a type system, pretty much like Shapeless does. And we also would like to have all our checks in compile time instead of runtime, right? Mm-hmm. So here, let me introduce you concept of session types. So basically, session types do the same for communication as types do for normal data. They codify the structure of the communication in the same way like normal types do for the data, and they make this structure available to programming tools and to programmer at the compile time. To be more concrete, what is it all about? It's very abstract. So I will just walk you through some very simple code, or just simple code, let it be like that. And to give a credit, we actually took an example from this paper of Martin Andersky and others, and augmented it a little bit with state analyzer. And so first of all, we need to encode our states. So we have a state, and we have a couple of states which is allowed for a parcel to have. Then we actually need to describe which state transitions are allowed. This one is important. The rest of the examples will be about this state transition, which is from package to sending. Yeah, we have a couple of others, but they are not relevant for this talk. And of course, this is a type class. Yeah? So basically, this is our parcel. Interesting part about this resource, it represents a resource with some properties, and it has state. And it does not have to implement anything else. The Scala can happily work with something which just has some state as a type. And yeah, of course, now we want to send this parcel, right? So we want our server to be able to receive this parcel in packaged state. We want to change its content, and we want to return some result back to the caller. After that, the server just wants to stop the communication. So, and it returns the desire to stop the communication and the result of calculation. Of course, if we have a server, we need a client. So that's our client. The client does exactly the opposite which server does. It actually constructs the parcel in initial state. It expects the communication to be stopped after the communication with the server, and it sends with this out a parcel to the server process, and it expresses his desire to finish the communication with this part. So what are those funny out and in on the previous slide? So we, in order to express our state, we need to be able to express the steps of those communication. Here we got 3 of them. This is a stop, this is an in, and an out. In is a server part. It expects a resource in some state. It advances its state from A to B, and this is an expected continuation of the communication between server and the client. It got a receive method which actually does the work. It gets the resource, returns the continuation, and resource in the new state. And this is needed in order to check that the state transition is allowed for the server to do. The out is much simpler. It just returns or gives us a resource in state A, and it informs us which continuation of the session it expects. Yeah. Now, as we have both of them, we can run this session. And of course, we need to implement this run session method, how it would look like. So we encode it as a session trait, and the session trait has actually 2 types. It has a self type S, and it has a dual type, because we have 2 processes which are mirroring each other. We cannot do in without out and the opposite. So basically this trait has a type S and it has a type dual, which we encode with this type constructor, which returns the session with a type S from here, and the dual encoded as a type T. Yeah. And we get some run method which our communication atoms need to implement. And then we can construct this run session method, which will describe its types. We can then take a session in some state, application state, and a dual of it. We can resolve implicitly the dual of this session using this type constructor, and we can run the session. And it actually doesn't matter if you run the session with a server and then client as parameter, or the other way around. They're really dual. So we need duals. For in, we need some dual of in. For out, we need some dual of out. And let's start with a stop. So the stop is a dual of our stop atom, and it extends the session with this state, and it basically does nothing. It's a static type. It's has nothing special in it. This one is more involved. So it's in dual, and of course the dual for in would be out. It got all of those states. It got implicit continuation, which compiler needs to resolve. And this guy, actually, this def, it's a polymorphic dependent, has polymorphic dependent type. What does it mean? It means that here, this continuation, we depend on it as a part of the continuation. So basically, all of this is a type of the continuation. Yeah, the run method is just receives the data from the opposite part, returns the continuation, and continues with a dual continuation. The out method is really very similar. It has a similar type depending on the continuation, and it really makes completely opposite stuff. It receives the data here and returns the continuation here and here. So we have a little bit more interesting example in this link, if you like to see how it works. And now how it works, it's basically we can load this Scala class, and then compiles, and we can run the session, and it runs, and then everybody's happy. So we can change something though, that in order we're doing something wrong. For example, we can close the post. So we make this transition impossible. In this case, we'll get at the compile time error message from the compiler that this transition is not allowed anymore. We can also try to skip the post step altogether and move the package parcel from package state to moving state directly. So in this case, compiler, of course, will inform us once again that this transition is not possible. So that's so much for our transition state, which should be valid. But the point is that the communication itself can be misaligned. In the sense, if we expect here a package in a parcel in sending state, and the client gives us a parcel in package state, then the server shouldn't be able to communicate with the client in this case. So, and that's exactly what happens. Here the error message is a little more involved, and basically here we see the full session type which cannot be resolved because of the wrong initial state of the parcel. And all this happens, of course, at compile time. In the same way, it will fail if we just add additional step the client is not expecting. So the server, instead of just stopping at this point, it tries to output something, and once again, the compiler says, yeah, that's not possible to find the dual of this communication in scope. So basically, we have everything in compile time. Everybody's happy, almost happy end. Do you want to take some questions?
Almost happy end. Almost happy end. Session types also already exist for a very long time. They really try to make, as shown, typesafe the communication. The easiest thing to think about them is that they are built up from 5 different types of primitives: sending, receiving, sequence, choice, and recursion. And what has been shown just was the way how to do it for sending and for receiving. So the in and the out, and the fact that they are dual towards each other. The implementation was with continuation passing style and with type classes. But if we need to map them on a RESTful and a hateful sense, then there is this possibility that the client at some point needs to choose from a hypermedia control, which it selected. And there we go into a problem, because 2010, Fun with Type Functions, Simon Python-Jones and others, he showed that in this way session types cannot be encoded and cannot be modeled. So basically, for session types, at least with this type of implementation, choice is not possible, and with that we can still not do it in a compile time static way and enforce the contract between the client and the server. So session types and REST, no, not really at the moment. It is work in progress, but we would like to say what are at this moment what we are thinking. Contract first, session types never, at least in a RESTful type of way. No API specification standard is really about REST. We all talk about this REST APIs. Basically, at least we are not aware of a standard which actually gives rules to say which hypermedia controls are coming. REST also allows for client-side contract checking, so that is a good part. One side can be enforced. And session types themselves, they don't really fit RESTful communications. Are there any questions? In that case, I'd like to thank you.